Hi, I'm Dr. Miguel Mitchell, founder of ChemAnimation.com. This is the first in the series of lectures for the course OChem 2 Intensive, and it's entitled Conjugation, FMO Theory, and Their Applications. First, what is conjugation? Conjugation is defined as the parallel, that is side-to-side, overlap of three or more adjacent p orbitals. These p orbitals can also include lone pair hybrid orbitals. In case 1, we have two isolated pi bonds. We have no more than two p orbitals adjacent to each other on either end of the molecule. Thus, the system is unconjugated. In case 2, the pi bonds are now next to each other. You have four p orbitals that are parallel and adjacent, and thus the system is conjugated. In case 3, we have two carbon-carbon double bonds which are fused to each other. This forces the two pi bonds to be perpendicular instead of parallel. Thus, there are no more than two p orbitals which have parallel overlap, and this molecule is unconjugated. And finally, in case 4, we have two examples of three parallel overlapping p orbitals. One which is an anion, so there's a lone pair now as part of the conjugated system, and the other which is a cation, so there's an empty p orbital as part of the conjugated system. So, three parallel overlapping p orbitals, all of which are adjacent to each other, allowing for conjugation. The parallel overlap of three or more adjacent p orbitals increases the stability of a molecule more than if those p orbitals were isolated from each other. To show you how conjugation increases the stability of a molecule, which means it lowers its potential energy, let's take a look at the heat of hydrogenation of a couple isomers. The heat of hydrogenation will decrease upon conjugation. In the case of the first isomer, it's unconjugated. The pi bonds are isolated from each other, and upon hydrogenation, you produce minus 52.5 kcal per mole of heat. In the case of the second isomer, now we have two adjacent pi bonds, so there's conjugation, four parallel adjacent p orbitals. And upon hydrogenation, we release only 45.9 kcals per mole of heat. Thus, there is a stabilization of this isomer compared to the previous one by about 6.6 kcal per mole. Now, is that all due to conjugation? No, there's a small amount, about 1 to 2 kcals per mole, caused by the additional substitution at the end of the double bond. But the rest of it is due to conjugation. Okay, let's consider one of the most important applications of conjugation, which is how conjugation can lead to substances having color. Here's a section of the electromagnetic spectrum. Starting from the left, we have the ultraviolet region, or UV, that's associated with sunburn, and this is light we can't see. Then we extend to the right into the visible spectrum, so all the colors that we can see with our eye, and then finally to the far right into the infrared spectrum, which is associated with heat. We can't see that either. Unconjugated molecules absorb in the high energy, short wavelength part of the ultraviolet spectrum, such as these two unconjugated alkenes, which absorb maximally between 177 to 181 nanometers. Lambda max refers to a peak of absorption, okay, a highest or maximum absorption that occurs for these molecules, and that's between 177 and 181. Put four p orbitals in conjugation with each other, and now we've increased the lambda max to 223.5 nanometers. Add another 4 p orbitals, so now we're up to 8 p orbitals in conjugation, and now our lambda max is up to 302 nanometers, getting closer to the visible region of the spectrum. Now we have beta-carotene, which has a whopping 11 conjugated pi bonds, or total of 22 conjugated p orbitals. Beta-carotene is the natural pigment of carrots, oranges, etc. It's orange because it has a lambda max of 463 nanometers. But strangely, as you can see, that's where the blue part of the visible spectrum is. So how come beta-carotene is orange? To explain how beta-carotene is orange, first we have to understand the parts of the visible spectrum. They start off at violet at 400 nanometers and go all the way to red, ending at 780 nanometers. The key thing is that when you absorb one kind of light, or different portions of the visible spectrum, you're going to reflect the rest of the visible spectrum, and that's what you're going to see. You're only going to see what's reflected, the leftover light. Our color wheel allows us to predict what light we will see, what's reflected at our eye, once we know what kind of light is being absorbed by the substance. The light that is being seen is always opposite or complementary to the color that is being absorbed. So they're always across from each other on the color wheel. With a lambda max of 463 nanometers, beta-carotene absorbs blue light, which means the color wheel tells us that beta-carotene should reflect orange light, which it does. So that's the color that we see of beta-carotene. This is the UV-vis, or ultraviolet visible absorption spectrum of beta-carotene. Absorbance is along the y-axis, and wavelength is along the x-axis in nanometers. If you look at that spectrum, it has a couple of peaks, and the peak that is furthest to the right at the higher wavelength is 463 nanometers. That's the wavelength that we associated with the blue light absorbance of beta-carotene. It also has a term, a constant, epsilon, which is 1.26 times 10 to the 5th liters per mole per centimeter. Now, what is that, and what does that have to do with how light is absorbed by beta-carotene? There's an equation called Beer's law, which is A, the absorbance, equals epsilon, the molar absorptivity, times the concentration C in moles per liter, times the path length L in centimeters. The path length defines the distance that the light has to travel through the substance when we're going to measure the absorbance. Usually we make a solution of the substance in some solvent and put it into a test tube or a cuvette, which is a kind of a square test tube, and the distance that's traveled by the light between the beginning and end of that cuvette or test tube is the path length. The larger that path length, the more the light's going to be absorbed. Molar absorptivity, as a constant, is a measure of how well the substance can trap that light and absorb it. So the larger the molar absorptivity, the more effective your molecule is at absorbing light at a given wavelength. In the case of beta-carotene, our spectrophotometer would be set to emit blue light, that's I naught, so that's the incoming blue light, at our cuvette, the little square container, which has a solution of the orange beta-carotene. The output blue light I is diminished because of the absorbance of blue light by the beta-carotene solution. We would measure the absorbance as being the log base 10 of the input light I naught divided by the output light I. This calculation of absorbance at different wavelengths is done automatically by your spectrophotometer. Let's take a look at an example of another dye, one that's used to stain fat in tissue samples, methylene blue. With lambda max values of 609 and 668 nanometers, methylene blue absorbs in both the red and orange regions of the visible spectrum. Again, we have our color wheel. Methylene blue absorbs on the red and orange side of the color wheel. So the color that we see that's reflected at our eye should be a mixture of blue and blue-green. Here is the UV-Vis absorption spectrum of methylene blue. You can see that there's a lambda max that peak at 668 nanometers. There's a little side hump around 600 nanometers, which should be about 609. That corresponds to the two lambda maxes for methylene blue, causing it to absorb both orange and red light. So if you look at the cuvette at the bottom, I0 represents that mixture of orange and red light that's coming through methylene blue. And we have a slower output I of orange and red light, which means that the actual color of methylene blue is some mixture of blue and blue-green. Why does conjugation increase lambda max?
Called frontier molecular orbital theory, or FMO, to explain it. Electrons act like waves. Now imagine an electron wave with a positive crest and a negative trough. If the crests or the troughs combine, there's an additive effect. Make the 2D electron wave a 3D atomic orbital, and these crests and troughs become orbital phases. The phases can be given positive or negative signs or opposite shading. Same phases combining head-to-head make a stable, low-energy molecular orbital or sigma bond. Now, if the positive crest combines with a negative trough, that cancels out the waves. In 3D, the head-to-head interactions of the atomic orbitals don't overlap, they repel, creating an unstable, high-energy, antibonding molecular orbital, sigma star. There is a region of zero electron density called a node between the atoms. For side-to-side overlap of p orbitals, you get a low-energy, stable molecular orbital, a pi bond, when the overlapping orbital phases are the same. If the interacting orbital phases are opposite, there's repulsion, and you get an unstable, high-energy, antibonding pi molecular orbital, pi star. Again, there is a node between the interacting orbitals, a region of zero electron density.
In FMO theory, a regular pi bond has two molecular orbitals. The low-lying HOMO, or highest occupied molecular orbital, has the two electrons in it that are part of bonding. Those two p orbitals overlapping have the same phase. There is also the higher energy unoccupied LUMO, the lowest unoccupied molecular orbital, where the two p orbitals have opposite phases and there's a node in between. The electrons have to be excited from the HOMO to the LUMO to be absorbed by light. There's a very large gap corresponding to the ultraviolet region of the spectrum. In the conjugated example of 1,3-butadiene, we have 4 overlapping p orbitals, which will create 4 molecular orbitals. The lowest lying molecular orbital, the lowest energy one, the ground state molecular orbital, will correspond to 4 p orbitals of the same phase in conjugation. That'll have 2 electrons in it. Now there are 2 more electrons that are part of the pi system, and they go into the slightly higher energy HOMO, the highest occupied molecular orbital, which has 1 node and 2 bonding pi interactions. So that's a net bonding interaction. Above that is the LUMO, the lowest unoccupied molecular orbital, which has 2 nodes. And then above that is the highest energy pi-type orbital, which has 3 nodes. We're only interested in the HOMO and the LUMO because those are the frontier molecular orbitals. Notice that the energy gap between the HOMO and the LUMO, the amount of energy that it will take to excite the electrons when they're absorbing light, is smaller now that we've had conjugation. So with conjugation, you decrease the gap between the HOMO and the LUMO and thus increase the wavelength necessary to absorb light. How do we know this? Well, delta E, that energy difference between HOMO and LUMO, is going to be equal to hc over lambda. H is Planck's constant, c is the speed of light, and lambda is the wavelength. Thus, delta E is inversely proportional to the wavelength. When you have a smaller energy gap between HOMO and LUMO, the wavelength of light that's needed to jump that gap to excite those electrons is larger. Conjugation also makes the molecule more stable because of the new ground state molecular orbital, which has much more overlap between the p orbitals. That lowers the potential energy of the molecule. Practice problem 1. Arrange the following compounds from smallest lambda max on the left to largest lambda max on the right and explain, using drawings of conjugated p orbitals in your explanation. You will want to pause the video now so that you can work on this practice problem. Answer to practice problem 1. Okay, what we're going to do is we're going to place all our p orbitals, that includes lone pairs, that are in conjugation and count them. We note that C has only 4 conjugated p orbitals, thus it should have the largest HOMO-LUMO gap and thus the smallest lambda max, so we put that on the far left. A has 5 conjugated p orbitals, the lone pair on the oxygen, 4 more p orbitals in conjugation, and the fused carbon-carbon double bond at the end is perpendicular, as you see, thus it is not part of the conjugated system. 5 is 1 greater than 4, so that's in the middle, so that has a slightly larger lambda max and a slightly smaller HOMO-LUMO gap. Now we have B, which has a total of 7 conjugated p orbitals, and thus the smallest HOMO-LUMO gap and the largest lambda max. Chromophores and oxychromes. Chromophores are the functional groups in the molecule that are responsible for light absorption at greater than 200 nanometers. They also allow you to absorb into the visible. So these would include the conjugated pi bonds, the nitro group NO2, the azo group N double bond N, and many others. Oxychromes do not absorb ultraviolet light at greater than 180 nanometers. Instead, they increase the wavelength and intensity of the light that's absorbed on a conjugated system. They include alkyl groups, oxygen, sulfur, nitrogen, the halogens, fluorine, chlorine, bromine, and iodine, a plus charge, which is part of conjugation, and a negative charge or lone pair is part of conjugation, negative charge having the larger wavelength increasing effect. In fact, the lone pair or negative charge increases the wavelength of light absorbed because it's in the N state, or energy equals 0 state, much closer to the antibonding orbital, which we call LUMO. Thus, that gives the HOMO-LUMO transition a smaller value. When a positive charge, that is an empty p orbital, is in conjugation with other pi bonds, what happens is that energy gap between the HOMO and LUMO decreases because the energy of the LUMO is decreased. When there is a negative charge as part of conjugation, such as a lone pair adjacent to a pi bond, what happens is that the energy of the HOMO is raised, it's increased, and that decreases the HOMO-LUMO gap. The push-pull effect is an extremely effective way to develop color in molecules. An electron pair donor, such as nitrogen or oxygen, resonates or pushes its electrons through conjugation to a good electron pair acceptor, which pulls those electrons in. such as C double bond X or C triple bond X, where X is more electronegative than C. Could also be N double bond O, S double bond O, etc. Something which is going to be able to withdraw electrons, pull electron density toward it. Now, in the case of N versus O as electron pair pushing agents, N would be better than O because N is less electronegative than O. In the example of 7-aminocoumarin, the lone pair on nitrogen pushes into the conjugated pi system all the way to the C double bond O, which pulls the electrons toward the O. This causes 7-aminocoumarin to be yellow, so the transition occurs in the visible region of the spectrum. If you compare that to beta-aminonaphthalene, that has 11 conjugated p orbitals, 2 more than 7-aminocoumarin, but beta-aminonaphthalene is still a colorless substance, only absorbing in the ultraviolet region of the spectrum. One further note, I didn't pick oxygen in 7-aminocoumarin to create my push-pull effect, and that's because oxygen is more electronegative than nitrogen, so it's going to have less of an ability to donate those electrons. In fact, coumarin itself, without the NH2 group, is colorless, so the push-pull effect of that oxygen is negligible. In conclusion, the push-pull effect lowers the lambda max more than 2 more conjugated p orbitals. So, if you have 9 conjugated p orbitals and a push-pull effect versus 11 conjugated p orbitals and no push-pull effect, the one with 9 conjugated p orbitals and a push-pull effect will have a lower lambda max. Right, we have 2 terms to learn: bathochromic and hypsochromic shifts. With a bathochromic shift, there is a structural change in the molecule that causes an increase in the lambda max, so that the energy gap between the HOMO and the LUMO decreases. For example, if you look at the initially colorless trityl chloride, when it dissociates in methanol, it will form a carbocation that has extensive conjugation. Unlike the previous compound, in which there were no more than 6 p orbitals in conjugation from the isolated benzene rings, now that empty p orbital is able to network with the other benzene rings, and we have as many as 13 p orbitals in direct countable conjugation. With a hypsochromic shift, a structural change causes a decrease in lambda max because that HOMO-LUMO gap now increases. For example, you can have the conjugated 1,3-cyclohexadiene reacting with hydrogen over a platinum catalyst to form the unconjugated cyclohexane molecule. In the original case, the conjugated system would absorb above 200 nanometers, and in the unconjugated case, well below 180 nanometers. Practice problem 2. Crystal violet, or gentian violet, also known as gram stain for staining gram-positive bacteria, has the following colors: no color at pH 10, blue violet at pH 7, which has a lambda max of 590 nanometers, and yellow at pH -1, the lambda max at 420 nanometers, and the molecule has an overall +3 charge. So you want to think about how it would get 3 positive charges. It already starts out with 1. So in part A, what colors are being absorbed by crystal violet at each pH other than pH 10? So when you look at the blue-violet situation and the yellow situation, you want to think about the color wheel. In part B, classify each color transition, no color to blue-violet and blue-violet to yellow, as either a bathochromic or hypsochromic shift, and explain. So go back and look at the definitions of those 2 terms. In part C, draw your predicted structure at each pH. Hint, there's a significant concentration of hydroxide at pH 10, right? That's 10 to the minus 4 molar hydroxide. Use, in part D, homo-lumo analysis to explain the changes in lambda max with decreasing pH and why crystal violet has no color at pH 10. We have to think about conjugation in these situations so that you can understand why there's no color at pH 10. You will want to pause the video now so that you can work on this practice problem. Answers to practice problem 2. In part A, we can use our color wheel to figure out what happens with different colors. The blue-violet color that's reflected at pH 7 is caused by the absorbance of yellow-orange light, and the yellow color reflected at pH -1 is caused by the absorbance of violet light. In part B, the compound with no color is absorbing the ultraviolet region, less than 400 nanometers, and that shifts to blue-violet, which means it's absorbing yellow-orange light, 570 to 620 nanometers. That's the sum of the two wavelength regions for yellow and orange. This is an increase in wavelength, therefore a bathochromic shift. Lambda max increases. Now when you go from the blue-violet, 570 to 620 nanometers, to yellow, yellow absorbs the violet color, which is 400 to 420 nanometers. That's a decrease in lambda max, therefore this is a hypsochromic shift. Part C. Alright, at pH 10 we have a compound that is colorless, which means that it's only absorbing UV light. That means we want to create a situation with the least amount of conjugation, and conclude that that's going to be insufficient to absorb visible light. So what we do is we draw a resonance which puts a plus charge in the center, flanked by all the benzene rings. At pH 10, there's enough hydroxide to attach to that positive charge, isolating the benzene rings, so that with the pi bonds in benzene and the lone pair on nitrogen, we have only 7 p orbitals in conjugation. At pH 7, we have a push-pull effect from 11 conjugated p orbitals and a conjugated plus charge. This is going to have the biggest impact on decreasing the homo-lumo gap and increasing lambda max into the visible spectrum. At pH -1, we're going to protonate those tertiary amines, removing those lone pairs from conjugation, which means you've eliminated the push-pull effect, which, remember, that's an extremely important effect for increasing your lambda max and making your molecule absorb in the visible region. So that even if you count the 12 conjugated p orbitals and a conjugated plus charge, your homo-lumo gap is going to be larger than the structure at pH 7, and the lambda max will decrease. So this is again a reminder of how important that push-pull effect is. Even with 12 conjugated p orbitals, one larger than the structure at pH 7, because we've eliminated the push-pull effect, we do not absorb at a longer wavelength. We actually absorb at a shorter wavelength.